That majestic spiral of stars in the night sky is a city of 100 billion suns. We are about to travel across space and time to uncover 50 astonishing truths behind these cosmic islands. You will discover the violent origins, the invisible forces that shape them, and the ultimate fate awaiting every galaxy, including our own. How did the entire universe grow from a formless soup into these intricate structures, and what mysterious, unseen substance holds them together? When you look up at the stars tonight, what story do you think they are trying to tell? Our story begins in a universe that was almost perfectly smooth. For hundreds of thousands of years after its explosive birth, all of existence was a searing, opaque fog. This was not a fog of water vapor, but a thick plasma of fundamental particles, a roiling ocean of energy where light could not travel freely. There were no clumps, no dense knots of matter, no grand designs. The entire cosmos was a nearly featureless soup, unimaginably hot and dense. This profound smoothness is the first and most crucial piece of our puzzle. How could such a uniform beginning possibly lead to the intricate cosmic cities we see today, the sprawling galaxies separated by vast voids of empty space? That smoothness held a secret, tiny imperfections, quantum ripples that would one day become the seeds of everything. Hidden within that smooth, hot soup of the early universe were the faintest of whispers. These were quantum fluctuations, random, microscopic ripples in the very fabric of reality. In our everyday world, such tiny effects are completely negligible, like a single grain of sand shifting on a vast beach. But in the first fraction of a second after the universe began, something incredible happened. A period of hyper-expansion called inflation stretched these quantum ripples across the entire cosmos. What was once microscopic became astronomically large. These stretched imperfections were variations in density, tiny patches where the universe was ever so slightly more crowded or more empty than average. They became the foundational blueprint for everything. Think of a perfectly smooth sheet of dough. If you could zoom in with a microscope, you would see tiny air bubbles and uneven textures. Now imagine stretching that dough to the size of a continent. Those tiny, insignificant bubbles would become vast, continent-sized hills and valleys. This is what inflation did to the infant universe. It took the quantum fuzz and magnified it, creating a cosmic landscape of gentle density hills. These hills were the universe's first and most important landmarks. They were places where gravity had a tiny head start. Over the next billions of years, gravity would relentlessly pull matter toward these slightly denser spots. The empty regions would grow emptier, and the crowded spots would grow into the first stars, the first galaxies, and the vast galactic walls we see today. The grand design of the cosmos, with its majestic spirals and brilliant clusters, began with a whisper. It is a profound connection between two seemingly separate worlds, the unpredictable realm of the quantum and the epic scale of the cosmos. How could something so small dictate the fate of something so unimaginably large? Yet that cosmic blueprint of density hills would have remained an unrealized plan without a hidden force. A mysterious substance completely invisible to our eyes and our telescopes provided the essential framework for construction. We call this substance dark matter. It is the universe's greatest unsolved mystery, a form of matter that does not emit, absorb, or reflect any light. We cannot see it directly, but we know it is there because of its powerful gravitational pull. Think of dark matter as an invisible scaffold. When the universe was young, normal matter, the stuff that makes up stars, planets, and us, was under immense pressure from the intense heat and radiation. It was like trying to build a sandcastle in a hurricane. The particles of light, called photons, were constantly slamming into the particles of normal matter, preventing them from clumping together effectively. Dark matter, however, was immune to this chaos. Because it does not interact with light, it felt only the gentle, persistent tug of gravity. It began to collapse into those primordial density hills long before normal matter could. It formed vast, invisible halos, creating deep gravitational wells. These wells became cosmic traps. The normal matter, swirling and hot, would eventually fall into these pre-existing pits of dark matter gravity. Once there, it could cool down, condense, and finally begin to form the first stars and the first proto-galaxies. Dark matter makes up about 85% of all the matter in the universe. This means the glittering galaxies we see are just the visible tips of immense, unseen icebergs. Every galaxy, including our own Milky Way, is embedded within a colossal sphere of this invisible material. Without dark matter's gravitational anchor, the universe would be a very different place. There would be no grand spirals, no brilliant elliptical galaxies, and likely no us. The very existence of galaxies as we know them is a direct result of this ghostly cosmic scaffolding. So the next great structure to form was not a star, but a dark matter halo, an invisible cradle waiting for the light to arrive. The invisible gravitational wells of dark matter finally gave structure to the chaos. Within these deep, unseen pits, the first true galaxies began to coalesce, but they were nothing like the majestic spirals we know today. Emerging only a few 100 million years after the Big Bang, these infant galaxies were the universe's pioneers, small, chaotic, and fiercely energetic. They were likely no larger than 1/100th the mass of our own Milky Way, mere cosmic villages compared to the vast cities of stars that would follow. Their shape was irregular and clumpy, lacking the elegant symmetry of a spiral's arms or the smooth sphere of an elliptical galaxy. They were, in essence, raw construction sites, dominated by vast reservoirs of pristine hydrogen and helium gas. This gas was the fuel for a furious burst of star formation, creating the universe's very first populations of stars. These first stars were not like our Sun. They were behemoths, hundreds of times more massive, burning ferociously bright and dying young in spectacular supernova explosions. These explosions seeded the surrounding gas with the first heavy elements, the very materials that would one day form planets and life. We can see this violent process play out in sophisticated computer simulations. They show these small, proto-galactic building blocks swarming in the dark matter halos, constantly drawn together by gravity. They do not simply drift apart, they collide, they merge, and they are torn asunder, a chaotic dance of creation and destruction. A single large galaxy like our own is not the product of a single quiet collapse. It is the archaeological record of thousands of these smaller galaxies crashing together and assimilating over billions of years. Every major galaxy we see today is a cosmic fossil built from these tiny, frenzied beginnings. These chaotic building blocks did not remain isolated for long. Their fate was to collide, and in these collisions we find one of the most powerful engines of galactic evolution. The growth of a galaxy is not a gentle, steady process. It is a story of violent unions, of cosmic construction sites where entire cities of stars are thrown together. When two galaxies meet, it is not the apocalyptic firework display we might picture. The distances between stars are so vast that direct stellar collisions are incredibly rare. Instead, the event is a slow, gravitational dance that unfolds over hundreds of millions of years. The galaxies first feel each other's pull, stretching out long, shimmering tidal tails of stars and gas, like the magnificent arcs seen in the antennae galaxies. These graceful streams are the first sign of a profound transformation. As the galactic cores swing past each other and eventually merge, their collective gravity acts like a giant blender. It violently churns the orbits of billions of stars, scattering them into a new, often spherical configuration. But the most dramatic effect is on the gas. Vast clouds of hydrogen, once peacefully orbiting in the galactic disks, are suddenly forced together. they are compressed, shocked, and funneled toward the center. This is the trigger for a spectacular phenomenon known as a starburst. In a relatively short cosmic time, the galaxy ignites with the furious birth of millions of new stars. It is a firestorm of creation, far more intense than the normal, quiet rate of star formation. These brilliant new stars are massive and hot, painting the merging galaxy in vivid blues and ultraviolet light. The merger essentially forces the galaxy to use up its remaining fuel reserves in one glorious, wasteful, and spectacular burst. The final product of this cosmic construction site depends on the original galaxies. Two large spiral galaxies crashing together will typically erase their beautiful disk structures, their stars tossed into a random, swirling haze. The result is often a new, featureless elliptical galaxy. This explains a long-standing mystery why we see both elegant spirals and smooth, round ellipticals in the sky. They represent different stages of a galactic life cycle shaped by violent encounters. Our own Milky Way is not immune to this process. It has consumed smaller galaxies in the past, and it is on a collision course with the neighboring Andromeda galaxy. Billions of years from now, these two great spirals will meet, and their merger will likely create a new, giant elliptical galaxy, a silent monument to a construction project that began with a whisper in the early universe. Those majestic spiral arms are not what they seem. They are grand cosmic illusions, not solid, spinning structures. If they were, the universe's most beautiful galaxies would simply wind themselves up and vanish over time. The outer stars orbit more slowly than the inner ones, so any physical arm would be stretched and twisted beyond recognition in just a few rotations. The solution to this winding problem is one of the most elegant ideas in all of astronomy, the density wave theory. Picture a traffic jam on a vast circular highway. The jam itself is a region of high density, a slow-moving wave of congestion. Cars enter the back of the jam, slow down, and then eventually speed up as they leave the front. The traffic jam moves around the highway at its own speed, independent of the individual cars. This is exactly how a spiral galaxy works. The majestic arms are not made of the same stars forever. They are rotating waves of compressed space, gravitational traffic jams that move through the galactic disk. As a cloud of gas and dust enters this dense wave, it gets squeezed. This compression is the trigger for star birth. The gas collapses under its own gravity, igniting into brilliant blue, short-lived stars. These massive hot stars are what make the spiral arms so brilliantly visible. They light up the wave, tracing its path before they explode as supernovae long before they can travel out of the arm. The stars themselves are just passing through. They enter the arm, linger for a while in this stellar traffic jam, and then exit on the other side, continuing their journey around the galaxy. The spiral arm is the pattern, not the participants. This beautiful, self-sustaining cycle gives a spiral galaxy its iconic structure, a brilliant pinwheel of ongoing creation. And just like a city, a spiral galaxy has distinct districts. At its heart lies the central bulge, a dense, spherical swarm of older, redder stars buzzing around the core like a vast beehive. Surrounding this is the magnificent disk, a flat, rotating plate where the spiral arms are etched, containing the younger stars and the gas and dust for new ones. And enveloping it all is the vast, diffuse halo, a giant sphere of ancient stars and the immense, invisible presence of dark matter, the hidden anchor for this entire cosmic metropolis. But those elegant spirals are only one type of galactic city. Look deeper into space and you will find a very different kind of giant. Elliptical galaxies are the universe's retirement communities, vast and serene collections of ancient stars. They lack the vibrant spiral arms and flat disks of their younger cousins. Instead, they appear as smooth, featureless, and often football-shaped spheres of light, glowing with a soft, golden red hue. This color is a direct clue to their nature. The red tint comes from their stellar population, which is overwhelmingly composed of old, cool red stars. There is no blue light from hot, young stars being born. The party of creation is long over in these regions. So how does a bustling, star-forming spiral galaxy transform into this quiet, aging elliptical? The answer lies in a violent past. Astronomers believe most elliptical galaxies are the final products of those major galactic mergers we discussed. When two gas-rich spiral galaxies collide, the event is catastrophic for their future. The collision triggers a ferocious but short-lived starburst, using up the available gas in a brilliant, final burst of fireworks. But more importantly, the immense gravitational turbulence of the merger effectively sterilizes the remaining gas. It can be flung out into intergalactic space, or it can be funneled directly into the supermassive black hole at the galaxy's center, powering a brilliant quasar that heats the surrounding material, preventing it from ever cooling down to form new stars. The galaxy is left gas-poor, its fuel reserves spent. With no raw material left for new stars, the galaxy's evolution grinds to a halt. The massive blue stars live short lives and die out quickly, leaving behind the longer-lived, older, redder stars. The chaotic merger also randomizes the orbits of billions of stars, wiping out any orderly disk structure and sculpting that smooth, elliptical shape. What remains is a cosmic fossil, a giant collection of aging stars silently orbiting for eons. The spiral galaxy was a dynamic, ever-changing metropolis. The elliptical is its magnificent but quiet monument. Not every galaxy fits neatly into the categories of elegant spirals or serene ellipticals. Some are the cosmic misfits, the irregular galaxies, lacking any symmetrical shape whatsoever. They appear as chaotic splatters of starlight, like paint flung across a dark canvas. These galaxies tell a different kind of story, one of disruption and raw, untamed creation. Some are the leftover building blocks from the early universe, small protogalactic fragments that never merged into a larger, more orderly structure. They are the cosmic equivalent of small, isolated villages that were never absorbed into a sprawling metropolis. But many other irregulars are the victims of cosmic bullying. When a small galaxy drifts too close to a much larger neighbor, the immense gravitational pull of the giant can violently distort it. The smaller galaxy is stretched and torn, its stars and gas pulled into long, streaming arcs, completely destroying its original shape. This gravitational harassment does more than just warp its form. It kick-starts a frenzy of activity. The same tidal forces that distort the galaxy also compress its vast reservoirs of gas, triggering an explosion of star birth. This is why irregular galaxies are often brilliant hotbeds of stellar formation, glowing with the intense blue light of young, massive stars. A perfect example hangs in our own southern sky, the Large Magellanic Cloud. It is a satellite galaxy of our Milky Way, and its distorted, blob-like appearance is a direct result of our galaxy's gravitational influence. Within its chaotic borders, immense nebulae like the Tarantula Nebula blaze with the light of thousands of new stars, a stellar nursery of staggering proportions. So while they may lack the majestic beauty of a perfect spiral, these irregular galaxies are cosmic laboratories of creation, showing us the ongoing, violent, and beautiful process of how gravity continues to sculpt the universe. The universe's chaotic menagerie of galaxies needed a filing system, and an astronomer named Edwin Hubble gave us one. His famous tuning fork diagram is like a family photo album for the cosmos, organizing galaxies by their shape. At the handle of the fork, you find the smooth, round ellipticals classified from E0, which are nearly circular, to E7, which are more oval or football-shaped. The diagram then splits into two prongs. One prong shows the majestic spiral galaxies, from those with large, bright central bulges to those with tight, small bulges. The other prong displays barred spirals, which have a distinct straight bar of stars cutting through their center, with the spiral arms unwinding from the ends of that bar. It is a beautifully simple way to bring order to the sky, but this classification holds a profound and common misunderstanding. The Hubble sequence is not a timeline of evolution. A galaxy does not start its life as an elliptical at the handle and then somehow morph along the prongs into a spiral. The shape of a galaxy is not about its age, but about its history and its environment. An elliptical galaxy is not a young spiral, and a spiral is not an old elliptical that grew arms. They are fundamentally different outcomes shaped by different lives. An elliptical is often the product of a violent merger, a cosmic collision that used up its gas and randomized its stars. A spiral, by contrast, is a more quiet, isolated existence where a stable disk of gas can slowly and steadily form new stars over billions of years. The tuning fork diagram is a snapshot of diversity, not destiny. It shows us the different forms a galaxy can take, each one a unique answer to the question of how matter assembles under the relentless pull of gravity. This cosmic predator is closer than you might think. Our own Milky Way, that graceful river of light in the night sky, has a hidden history of violence. Far from being a serene island universe, our galaxy is a cannibal, growing over billions of years by consuming its smaller neighbors. We are living inside a galactic giant that has devoured countless dwarf galaxies throughout its long life. The evidence for this is written in the stars themselves, in vast, faint streams that wrap around our galaxy like celestial spiderwebs. One of the most dramatic ongoing mergers is with the Sagittarius dwarf spheroidal galaxy. This small galaxy has been caught in our Milky Way's immense gravitational pull, and it is currently being ripped apart. As it orbits, the tidal forces strip away its stars, scattering them into two magnificent streams that completely encircle our galaxy. It is a slow-motion dissection playing out over hundreds of millions of years, but this is not the first time such an event has occurred. Astronomers have mapped other, more ancient stellar streams, the ghostly remnants of galaxies that were fully consumed long ago. One of the most significant is known as the Gaia sausage, the remains of a massive dwarf galaxy that slammed into the young Milky Way around 8 to 10 billion years in the past. This colossal collision did not just add stars, it fundamentally reshaped our galaxy, puffing up its central bulge and contributing a vast population of stars to its halo. Every time the Milky Way consumes one of these satellites, it gains more than just stars. It acquires fresh gas to fuel new generations of stars, and it gains a burst of gravitational energy that stirs up its structure. This process of galactic cannibalism is how all large galaxies grow. They do not form in isolation, they are assembled from smaller pieces, a relentless accumulation of cosmic territory. So when you gaze at the seemingly peaceful band of the Milky Way, remember you are looking at a dynamic and ever-changing structure, a celestial empire built on the ruins of its former rivals. Our galaxy's history of cosmic cannibalism points toward its ultimate destiny. 4.5 billion years from now, the Milky Way will experience its final and most spectacular merger. It is on a direct collision course with the Andromeda Galaxy, our closest large galactic neighbor. Right now, Andromeda is hurtling toward us at a staggering speed of about 110 kilometers per second. This is not a chance encounter, but an inevitable embrace dictated by the mutual gravitational pull between these two titans. While the time scale is almost incomprehensibly vast, the outcome is certain. The two spiral galaxies will begin to pass through each other, their gravitational forces warping their beautiful structures beyond recognition. Long, shimmering tidal tails of stars will be flung out into intergalactic space, and the orderly dance of their stellar disks will be thrown into chaos. The cores of the galaxies, each harboring a supermassive black hole, will swing past each other in a series of close encounters before finally settling into a slow, spiraling dance. Over the next 1 to 2 billion years after the first encounter, they will completely merge, their stars and dark matter halos coalescing into a single new galaxy. Astronomers have already given this future giant a name, Miltromda. It will likely be a massive elliptical galaxy, a smooth, featureless sphere of ancient stars, a quiet monument to the violent union that created it. But what does this mean for our solar system? The vast emptiness of space within galaxies makes the prospect of stellar collisions almost non-existent. The average distance between stars is so immense that you could think of it as two swarms of bees flying through each other from opposite sides of an entire continent. The chance of any two stars colliding is virtually zero. Our Sun and its planets will likely be flung into a new, wider orbit within the chaotic new galaxy, but they will remain entirely intact. The night sky from Earth, however, will be transformed beyond all recognition. Instead of a faint smudge of light, the Andromeda Galaxy would grow larger and larger, eventually filling the entire heavens with a spectacular, swirling tapestry of alien stars and cosmic dust, a breathtaking prelude to the final merger. At the violent heart of every great galactic city lies a hidden monster. Nearly every large galaxy, including our own Milky Way, hosts a supermassive black hole at its very center. These are not the ordinary black holes formed from collapsing stars, but behemoths with masses millions or even billions of times that of our Sun. Our own resident giant is called Sagittarius, a star, a gravitational trap buried deep within the galactic core, silently anchoring our spiral journey. For a long time, astronomers thought of these central black holes as mere curiosities, bizarre inhabitants of a galaxy's downtown. But then they discovered something astonishing, a profound connection that hints at a shared history. The mass of a galaxy's central black hole is intricately linked to the properties of the galactic bulge, that dense, spherical swarm of old stars at its heart. In galaxies with larger, more massive bulges, the central black hole is also more massive. This correlation is too precise to be a coincidence. It suggests that the growth of the black hole and the growth of the galaxy itself are fundamentally intertwined, a process of co-evolution. How could an object so small, relative to the immense scale of a galaxy, possibly influence its entire development? The answer lies in a feedback cycle of unimaginable power. When a supermassive black hole actively feeds, drawing in vast quantities of gas and dust, it does not do so quietly. The infalling material swirls into an incredibly hot, bright disk around the black hole, blazing with the light of billions of stars, becoming what we call a quasar. This furious activity unleashes tremendous energy, shooting out colossal jets of radiation and matter. These powerful outflows act like a cosmic thermostat. They blast through the galaxy, heating the surrounding gas and driving it away. This effectively shuts down star formation by robbing the galaxy of the cold gas needed to make new stars. The black hole, in its most violent feeding state, ultimately quenches its own future food supply and regulates the growth of the entire galactic core. It is a self-limiting cycle, a dance of creation and destruction where the monster in the middle helps shape the very city that contains it. This intricate relationship means a black hole is not just a passive occupant, it is an active architect, its growth and activity written into the history of the stars surrounding it. When that central black hole feasts, the galaxy's core transforms into a cosmic powerhouse. This active state is what astronomers call an active galactic nucleus, or a GN. It is one of the most energetic phenomena in the universe, capable of unleashing more light than every star in its host galaxy combined. The process begins when vast quantities of gas, dust, and even entire stars stray too close to the gravitational monster. Instead of falling straight in, this material forms a frenzied, superheated accretion disk, spinning at nearly the speed of light. Friction within this disk heats it to millions of degrees, causing it to glow with the intensity of billions of suns. But the true spectacle lies in the jets. Perpendicular to the disk, the black hole can fire out colossal beams of radiation and subatomic particles, stretching for thousands of light years into space. The specific type of a GN we see depends entirely on our viewing angle. If we are looking face-on at the brilliant accretion disk, we see a quasar, a point of light so luminous it can drown out its entire galactic home. If one of those powerful jets is pointed almost directly at Earth, we call the object a blazar. A blazar is even more extreme, its jet-dominated emission violently fluctuating and pouring incredible energy across the electromagnetic spectrum. These are not different monsters, merely different views of the same incredible engine. For a long time, quasars were mysterious, star-like points of light in distant realms. We now understand they are the brilliant beacons of young galaxies in their most volatile and formative stages, their central black holes gorging on the abundant gas from the chaotic early universe. They are the universe's most powerful lighthouses, shining across billions of light years to tell us a story of cosmic awakening and unimaginable power. Yet for all their immense power, even supermassive black holes cannot contain all of a galaxy's raw energy. The life cycle of stars themselves creates a system of cosmic recycling that is vital for the galaxy's future. A galaxy is not a sealed box. It is a dynamic ecosystem where material is constantly being expelled and recaptured in a process known as a galactic fountain. Imagine a city not just with buildings, but with geysers that periodically shoot water high into the sky, where it cools and rains back down to nourish the streets below. This is how a galaxy replenishes itself. The driving force comes from the most massive stars and their spectacular deaths. When these giants go supernova, or when they blast out powerful stellar winds during their lives, they act like cosmic bombs. These explosions and outflows inject tremendous energy into their surroundings, heating the surrounding gas and flinging enormous bubbles of it clear out of the galactic disk. This hot, enriched gas shoots high up into the galactic halo, thousands of light years above the starry plane. Up in this colder, thinner environment, the gas begins to cool and condense. Losing its energetic push, it succumbs to the galaxy's relentless gravity. It then falls back down, raining onto the disk in vast, cool clouds. This is the fountain's complete cycle, an essential loop of expulsion and return. But this process does more than just move gas around, it fundamentally enriches it. The gas that was ejected was forged in the nuclear furnaces of massive stars, filled with newly created heavy elements like oxygen, carbon, and iron. When this material falls back as a cosmic rain, it seeds the interstellar medium with the ingredients for rocky planets and for life itself. The iron in your blood and the calcium in your bones were once part of such a cycle, ejected from a long-dead star in a galactic fountain, only to fall back down and become part of our solar system. This continuous recycling turns the galaxy into a living engine, where the death of one generation of stars directly provides the building blocks for the next. Those silent, invisible halos of dark matter leave a clear signature in the motion of the stars themselves. Picture a vast spiral galaxy like our Milky Way, with billions of stars tracing orderly orbits around its brilliant center. You would naturally expect the stars farther out in the galactic suburbs to move more slowly than those closer to the downtown core, just as Pluto orbits our Sun much more leisurely than Mercury. This is the simple rule of gravity that governs our solar system. But when astronomers first measured the actual orbital speeds of stars and gas clouds in distant spiral galaxies, they found something astonishing, a paradox that shook the foundations of modern astronomy. The stars in the outer regions were not slowing down. They were hurtling around at nearly the same incredible speed as the stars closer in. This data, plotted on a graph, creates a rotation curve that stays flat far out into space where the visible starlight all but fades away. According to the laws of physics, for these outer stars to be moving so fast without flying off into the void, there must be a tremendous amount of additional gravity holding them in their orbits. But when we add up all the visible mass, all the stars, gas, and dust in the galaxy, there is simply not enough gravity to account for their motion. the only logical conclusion is that the galaxy is enveloped in a massive, invisible sphere of something that provides this extra gravitational glue. We cannot see this dark matter halo, but we can watch the stars themselves betray its presence, their unexpectedly swift orbits tracing the outline of a ghost. Our galaxy is not a solitary island drifting in an empty sea. It is part of a community, a gravitationally bound family known as the local group. This is our cosmic neighborhood, a collection of more than 50 galaxies all held together in a delicate dance by their mutual gravity. The Milky Way and the Andromeda Galaxy are the two dominant giants in this group, with a host of smaller satellite galaxies like the Large and Small Magellanic Clouds orbiting them. But even our local group is just a small gathering in a much vaster cosmic metropolis. If we zoom out farther, we see that these groups themselves are part of something colossal, a galaxy cluster. These are the largest structures in the universe held together by gravity. A rich cluster can contain thousands of galaxies, all swarming around a common center in a space tens of millions of light years across. The nearest great cluster to us is the Virgo cluster, a sprawling city of galaxies containing over 1,000 members. Imagine the night sky from a planet inside that cluster. It would be filled with dozens of nearby galaxies, each as bright as our own Milky Way appears to us, creating a tapestry of nebulous light that would dwarf the constellations. But what holds these immense structures together? The combined gravity of all the visible galaxies is not nearly enough to bind the cluster. Once again, we find the invisible hand of dark matter at work. Galaxy clusters are embedded within immense halos of this mysterious substance, whose overwhelming gravity provides the cosmic glue that keeps thousands of galaxies from flying apart. These clusters are not static, they are dynamic environments where galaxies interact, sometimes even merging within the cluster itself. They represent the final, largest scale of cosmic structure, the great archipelagos in the ocean of space. The space between galaxies in a cluster is a far cry from the cold, silent void we might imagine. It is filled with a superheated, thin soup of gas known as the intracluster medium. This plasma is unimaginably hot, reaching temperatures of tens of millions of degrees, so fierce it does not glow with visible light but instead shimmers with powerful X-rays. When astronomers first pointed X-ray telescopes at galaxy clusters, they were stunned to find these colossal, glowing halos of ultra-hot gas, revealing that the true structure of a cluster is defined not just by its galaxies, but by this scorching, intergalactic ocean. In fact, this diffuse, searing plasma contains the majority of the normal matter, the baryons, in the entire cluster. There is more raw material for future stars and planets floating in this invisible, hot soup than there is locked inside all the thousands of galaxies combined. This raises a fascinating puzzle. How did this gas become so incredibly hot? The answer lies in the violent formation of the cluster itself. As galaxies and dark matter fell into the cluster's immense gravitational pull over billions of years, they gained tremendous speed, crashing together in a chaotic gravitational collapse. This process acted like a cosmic forge, converting that immense gravitational energy into heat and effectively pressure cooking the gas that was trapped between them. This discovery fundamentally changed our understanding of where ordinary matter resides, showing us that the glittering galaxies are just small, dense islands in a vast, invisible, and surprisingly heavy sea. This discovery of the searing intracluster gas was a monumental clue, but it pointed toward a universe even stranger than we had imagined. For decades, astronomers were certain about one thing: the expansion of the cosmos, set in motion by the Big Bang, must be slowing down. The collective gravity of every galaxy, every star, and every invisible wisp of dark matter was pulling on the fabric of space-time, acting as a cosmic brake. The only question was how quickly this deceleration was occurring. To find out, two independent teams set out to measure the universe's expansion rate over vast cosmic time. They used a special kind of stellar explosion, a Type 1 supernova, as a standard candle. These supernovae have a known intrinsic brightness, so by measuring how dim they appear from Earth, astronomers can calculate their precise distance. They can also measure how much the light from these explosions has been stretched or red-shifted by the expansion of space. By comparing distant supernova, which exploded billions of years ago, to closer, more recent ones, they could map the expansion history of the universe. The results, announced in the late 1990s, were not just surprising, they were revolutionary. The data revealed that the most distant supernovae were fainter than expected. This meant they were farther away than they should have been if the universe had been slowing down. The stunning conclusion was that the expansion of the universe is not decelerating at all. It is accelerating. Something was overpowering the collective gravity of the entire cosmos, pushing galaxies apart from one another at an ever-increasing rate. This mysterious, repulsive force was named dark energy. It is now understood to be the dominant component of our universe, making up about 68% of everything that exists. Dark matter, for all its mystery, accounts for about 27%, and all the normal matter, everything we can see and touch, makes up a mere 5%. The fate of galaxies on the largest scales is not to fall together, but to be driven apart by this invisible, repulsive pressure woven into the very fabric of space itself. Edwin Hubble's discovery tore apart the idea of a static, eternal cosmos. Peering through the Great Telescope at Mount Wilson, he noticed something peculiar about the faint, fuzzy nebulae that we now know are distant galaxies. The light from nearly all of them was stretched, shifting its color toward the red end of the spectrum. This phenomenon, called redshift, is a cosmic version of the Doppler effect. Just as the sound of a receding ambulance siren drops in pitch, the light from a galaxy moving away from us stretches to longer, redder wavelengths. Hubble and his colleague, Milton Humason, meticulously measured this redshift for dozens of galaxies. They paired this with difficult estimates of each galaxy's distance. The result was a staggering correlation. The greater the redshift, the farther away the galaxy was. This simple, direct relationship is now known as Hubble's law. It meant that space itself was not static but dynamically stretching, carrying galaxies along with it like raisins in an expanding loaf of bread. The entire universe was growing larger. This single observation was the first direct observational evidence for the Big Bang theory. It provided the stunning backdrop for everything we had discussed, from the primordial density fluctuations to the formation of galaxy clusters. The universe had a definite beginning, and it has been evolving and expanding ever since. This grand realization frames every story of galactic birth and death, placing them all within a single, unfolding narrative of cosmic evolution. Every observation we make of the cosmos is a journey into history. That faint smudge of the Andromeda Galaxy is not how it appears tonight, but a portrait from 2.5 million years in the past. Its light has been traveling through the void for all that time, finally reaching our eyes now. This is the ultimate time machine built into the very laws of physics. Because the speed of light, while incredibly fast, is finite, it takes time to cross the vast gulfs between galaxies. When astronomers point their telescopes at a galaxy 1 billion light-years away, they are not seeing its current state. They are witnessing a snapshot of that galaxy as it was 1 billion years ago, from an era when dinosaurs still roamed the Earth. This profound fact transforms our entire view of the universe. We are not limited to studying galaxies just as they are today. By looking out into deep space, we are also looking back in time. A galaxy 5 billion light-years away shows us its adolescence. 10 billion light-years away reveals its chaotic infancy. We can directly witness galactic evolution by simply observing the sky at different depths. Nearby galaxies like Andromeda show us mature, settled systems. but the most distant galaxies, whose light has been traveling for over 13 billion years, appear small, blue, and violently active, caught in the throes of their formation. This is how we know the early universe was a place of frenzied construction, with frequent collisions and intense bursts of star birth. Our telescopes are not just instruments of observation, they are windows to different chapters of the cosmic story, allowing us to watch the life cycle of galaxies unfold across the eons. This cosmic dawn of the first stars and galaxies tore the universe out of its dark ages. For hundreds of millions of years, the cosmos was a silent, opaque realm, filled with a thick fog of neutral hydrogen gas that trapped light. Then a profound transformation began. The earliest stars and galaxies ignited, and they were not like our gentle sun. They were colossal, ferociously hot, and blazed with intense ultraviolet radiation. This radiation acted like a cosmic blowtorch, striking the surrounding hydrogen fog and violently stripping electrons from their atoms. This process, called ionization, began to carve transparent bubbles in the opaque mist. Imagine a dense, freezing fog slowly lifting as countless lighthouses switch on one by one. At first, isolated bubbles of clear space appeared around each of these first luminous objects. Over time, these bubbles grew and merged, their edges meeting and dissolving the remaining patches of fog. This was the epoch of reionization, a fundamental phase change for the entire universe. It was the moment the cosmos became transparent, a clear window through which light could finally travel freely across vast distances. Without this pivotal event, the light from all subsequent galaxies would still be trapped, and the universe would remain a dark, impenetrable mystery to our telescopes. We are only able to see the ancient light from the most distant quasars and infant galaxies because of this great clearing that occurred over 13 billion years ago. That ghostly rain of gas falling back into the galaxy is not always a certainty. Sometimes the galactic fountain becomes a fire hose and the galaxy loses its lifeblood forever. These are galactic winds, powerful outflows so intense they can blow a galaxy's entire reservoir of star-forming gas right out into the emptiness of intergalactic space. This process, called quenching, is the ultimate shut-off switch for a galaxy's vibrant life. It transforms a bustling, blue, star-forming metropolis into a quiet, red, and dead retirement community. The engines for these cosmic gales are twofold. The combined fury of countless supernova explosions can generate these winds, their collective energy heating the surrounding gas to millions of degrees and driving it outward. But an even more potent force comes from the central supermassive black hole. When it is in its active quasar phase, the immense energy it releases can push against the infalling gas with far greater power than gravity can pull it in. This creates a feedback loop of staggering scale, where the black hole's own feast unleashes a hurricane that blows away its future meals and starves the entire galactic core of new material. We can see this dramatic process in action. In some distant galaxies, telescopes have captured vast bubbles of gas, millions of light years across, being expelled at speeds of thousands of kilometers per second. Once this gas is lost to the immense void between galaxies, it is almost impossible to recapture. The galaxy's primary fuel tank is empty. Star formation grinds to a halt. The massive blue, short-lived stars quickly burn out, leaving behind only the older, redder, longer-lived stars to glow with a dimming crimson light. This is the fate of many massive elliptical galaxies. Their star-making days ended not with a whimper but with a cosmic gale. The very forces that create stars in their most extreme form can also bring about their end. The furious dance of colliding galaxies does not just destroy, it can also create. When two great spirals swing past each other, their immense gravitational pull acts like a cosmic sculptor, stretching out vast, shimmering rivers of stars and gas. These are the majestic tidal tails, often arcing for hundreds of thousands of light years into the intergalactic void. For a long time, astronomers saw these beautiful structures as mere ephemeral features, destined to eventually fade back into the merged galaxy or dissipate entirely. But then they noticed something peculiar. Some of the densest knots within these tidal tails were not just random clumps, they were glowing with the distinctive blue light of newborn stars. These were not just streams of debris, they were stellar nurseries on an epic scale. In a stunning reversal of expectations, these knots of gas and stars can sometimes collapse under their own local gravity, pulling themselves together to form entirely new, independent galaxies. These are tidal dwarf galaxies, cosmic orphans born from the wreckage of a galactic collision. They are fundamentally different from the primordial dwarf galaxies that orbit larger hosts. Those ancient dwarfs are dominated by dark matter, their stars swarming within an invisible, massive halo. But a tidal dwarf galaxy is born from the disk material of its parent spirals, material which was already largely stripped of its dark matter. The result is a galaxy that is unusually rich in the gas needed to form stars, but surprisingly poor in the invisible gravitational glue. It is a celestial phoenix rising not from fire, but from the gravitational chaos of a crash. This means the very forces that can tear a galaxy apart also possess the creative power to assemble entirely new worlds from the pieces, proving that in the cosmos, endings and beginnings are often one and the same. From the cosmic wreckage of tidal dwarfs, we venture into a realm of even greater mystery, the ghost galaxies. Scattered throughout the cosmos are vast, ethereal islands known as ultra-diffuse galaxies. These are cosmic paradoxes, galaxies that can span the same immense diameter as our own Milky Way, yet they contain barely 1% of its stars. Imagine a city as sprawling as New York, but with only the streetlights of a small town, its vast avenues and towering structures lost in profound darkness. This extreme faintness makes them incredibly difficult to detect, like trying to spot a wisp of smoke against a dark night sky. The most famous of these phantoms is a galaxy called Dragonfly 44. When astronomers finally measured its mass, they were stunned. Despite having almost no stars, its gravitational pull was immense, indicating the presence of a colossal, unseen anchor. Dragonfly 44 appears to be made almost entirely of dark matter, a ghostly giant whose visible stars are merely incidental decorations on an invisible, massive frame. But the plot thickens. Other ultra-diffuse galaxies discovered in crowded galaxy clusters show the exact opposite behavior. They appear to be almost completely devoid of dark matter. This is a direct challenge to everything we thought we knew about galaxy formation. How can you have a galaxy that is the size of the Milky Way with so few stars and not be dominated by the dark matter halo that supposedly guides its very creation? One theory suggests these dark matter, poor phantoms are the stripped remnants of larger galaxies, their stars stretched thin and their dark matter torn away by the immense gravitational tides of a cluster. Another idea proposes they are failed galaxies, born in dark matter halos that were somehow too spin-heavy or too warm to condense their gas into many stars. These faint, sprawling ghosts force us to question the fundamental rules of cosmic construction, proving that the universe always has another surprise waiting in the shadows. Some galaxies wear their history like a perfect cosmic bullseye. Ring galaxies are among the rarest and most striking structures in the universe, appearing as a brilliant circle of young, blue stars surrounding a calm, golden core. The most famous example is Hoag's object, a galaxy that looks less like a natural formation and more like a piece of celestial art, a perfect loop of starlight adrift in the void. This remarkable shape is not the result of a gentle process, but of a violent and precise cosmic collision. The leading theory suggests that a smaller galaxy, billions of years ago, shot directly through the center of a larger, normal spiral galaxy, like a bullet passing through the bullseye of a target. The intruder did not collide with many stars, but its gravitational disturbance was immense. As it passed through the disk, its gravity violently tugged on the stars and gas, sending a powerful wave of compression rippling outward through the galactic disk. Think of tossing a single, perfect pebble into a still pond. The impact creates a circular wave that expands outward from the center. In a galaxy, this wave is a propagating ring of dense gas. As the wave travels outward, it squeezes the interstellar gas it encounters, triggering a firestorm of star formation. The massive, hot, blue stars born in this wave light up the expanding ring, while the galactic center, left behind and relatively undisturbed, continues to host its older, redder stellar population. The result is that breathtaking bullseye, a snapshot of a single, violent event frozen in time, its ripple of creation still visibly echoing across space. There is a cosmic shape that defies easy classification, a galaxy caught between two identities. Lenticular galaxies present a profound puzzle, possessing the central bulge and flat disk of a spiral, yet they lack the defining spiral arms and glow with the quiet, red light of an elliptical. They are designated as S0 on Hubble's tuning fork, a shape that seems to bridge the gap between the two main branches. So what story does this hybrid form tell? One compelling idea is that lenticulars are spiral galaxies in retirement. A spiral's vibrant blue arms are fueled by cold gas, the raw material for new stars. If that gas is removed or used up, the spiral arms, which are patterns of star formation, simply fade from view. The existing stars in the disk remain, orbiting peacefully, but no new blue stars are born to trace out the majestic patterns. The galaxy's star-forming factory has shut down. How does a spiral galaxy lose its gas? There are several paths to this quietus. It might drift into the dense environment of a galaxy cluster, where the searing heat of the intracluster medium acts like a cosmic blowtorch, boiling away its cold hydrogen fuel in a process called ram pressure stripping. Alternatively, a series of gentle interactions with neighboring galaxies could slowly siphon away its gas reserves over eons. Or it may have simply used up its gas in a final, moderate burst of star formation, exhausting its fuel without the violence of a major merger. This would leave the galactic disk intact but dormant, a fossilized record of its once active spiral structure. This makes lenticular galaxies potential missing links, capturing the moment a vibrant spiral settles into the serene, red and dead existence of an elliptical, but without the gravitational violence that typically randomizes a galaxy's stars into a full elliptical shape. They are the cosmic equivalent of a bustling city that has halted new construction, its streets and infrastructure still visible, but its light slowly dimming toward a permanent sunset. Even as our galaxy spins in its stately dance, it is also racing toward an unseen destination. Our entire local group, including the Milky Way and Andromeda, is not drifting aimlessly, it is falling. We are being pulled toward a mysterious, colossal concentration of mass that astronomers call the Great Attractor. This immense gravitational anomaly lies in the direction of the Centaurus constellation, a region of the sky that happens to be obscured by the thick dust and stars of our own galaxy's central bulge. It is as if the most important landmark in our intergalactic neighborhood is hidden behind a permanent cosmic mountain range. For a long time, its true nature was veiled from our view. We could not see it directly with optical telescopes, but we could feel its pull. By meticulously mapping the motions of thousands of galaxies across our cosmic vicinity, astronomers detected a vast river of galaxies, all flowing in the same direction, like leaves caught in a grand intergalactic current. This coherent motion betrayed the presence of a gravitational force so immense it could override the general expansion of the universe on a local scale. The Great Attractor is not a single object but a massive gravitational focal point, a node in the cosmic web where the density of both dark and normal matter is extraordinarily high. Its influence stretches across hundreds of millions of light years, orchestrating the motion of countless galactic islands. What secrets lie hidden behind the Milky Way's dusty disk, and what does this colossal pull mean for our ultimate journey through the cosmos? This galactic cannibalism reaches its most extreme form in the dense, violent hearts of galaxy clusters. Here, at the very center of these cosmic metropolises, reigns a true giant, a galaxy so immense it defies ordinary classification. These are the CD galaxies, colossal ellipticals that can be up to 10 times larger than our Milky Way, and they dominate their surroundings with overwhelming gravity. Their growth is fueled by a relentless and brutal process. In the crowded core of a cluster, thousands of galaxies swarm at incredible speeds, and the central CD galaxy acts as the ultimate cosmic predator. Its immense gravitational field creates a destructive zone around it. Any smaller galaxy that wanders too close is caught in an inescapable tidal grip. The smaller galaxy is stretched and deformed, its stars stripped away and pulled into long, shimmering streams that are gradually absorbed by the giant. This is not a fast, dramatic collision, but a slow, systematic dismantling, a gravitational feast that can continue for billions of years. The CD galaxy grows ever larger and more diffuse, its light fading into a vast, faint halo that can envelop the entire cluster core. This process explains why the very centers of rich clusters are so often dominated by a single, monstrous galaxy, a silent titan that has built its empire on the ruins of its neighbors. The environment a galaxy lives in writes its destiny. Look across the cosmos and you will notice a striking pattern. The shape of a galaxy is rarely an accident. Dense, bustling galaxy clusters are the domain of the smooth, red ellipticals and the quiet lenticulars. These are the galactic retirement communities where star formation has largely ceased. Venture out into the quieter cosmic countryside, the so-called field environments, and you will find a different population altogether. Here, the elegant spiral galaxies and the chaotic irregulars thrive, glowing with the vibrant blue light of ongoing stellar birth. This profound connection between a galaxy's form and its cosmic zip code is known as the morphology-density relation. It tells us that a galaxy's evolution is not just determined by its internal dynamics, but is powerfully shaped by its neighbors and surroundings. In the crowded core of a cluster, galaxies are constantly jostling, their gravitational fields interacting in a relentless dance. These frequent, high-speed encounters, known as galaxy harassment, can strip away a spiral's precious gas reserves or gravitationally stirred stars, disrupting its delicate disk and pushing it toward a more rounded, elliptical shape. Furthermore, the galaxy must plow through the cluster's own superheated atmosphere, the intracluster medium. This searing plasma acts like a cosmic wind, violently blowing the cold gas out of a spiral galaxy in a process called ram pressure stripping. It is like driving a car through a torrential downpour where the fuel tank is ripped open and drained dry. Deprived of its star-forming fuel, the spiral's arms fade, its blue stars die out, and it is left a red and silent relic. In the isolated field, however, a spiral galaxy can enjoy a quiet, undisturbed existence. It can hold onto its gas, slowly and steadily converting it into new stars over billions of years, maintaining its beautiful pinwheel structure. The universe, it seems, has a powerful way of imposing conformity in its most crowded cities, while allowing for individuality and vibrant life in its spacious suburbs. Our position in the Milky Way may be more than just a cosmic accident. The concept of a habitable zone extends beyond individual stars to encompass the entire galaxy. Just as a planet must orbit at the right distance from its sun for liquid water to exist, a star system might need to reside in the right galactic neighborhood for complex life to arise and survive. This idea defines the galactic habitable zone, a theoretical band where conditions are just right, too close to the bustling galactic center, and the environment becomes lethally chaotic. The density of stars is so immense that a nearby supernova, a frequent occurrence in such crowded quarters, could bathe a world in sterilizing radiation long before life could gain a foothold. The intense gravitational pull from the central supermassive black hole also stirs the pot, disrupting planetary orbits and creating an unstable environment. Venture too far out into the galactic hinterlands, however, and you face a different problem. The outer reaches of a galaxy are metal-poor, meaning they lack a sufficient abundance of heavy elements forged in the hearts of earlier stars. Without these elements, you cannot form rocky planets like Earth or the complex chemistry that life requires. Our own solar system orbits within this privileged middle ground, about halfway between the crowded core and the sparse outer rim. We are far enough from the galactic center to avoid its constant violence, yet we are close enough to be enriched by the heavy elements scattered by generations of stars that lived and died before our sun was born. This galactic sweet spot offers a stable orbital environment, a relative calm from stellar catastrophes, and the necessary planetary building blocks. It prompts a profound question: is our place in this quiet spiral arm a fundamental prerequisite for our existence, or merely a fortunate roll of the cosmic dice? The story of our galaxy is written in starlight, but you need to know how to read it. Galactic archaeology deciphers this cosmic history by treating the Milky Way as a vast dig site, with every star and artifact holding clues to a forgotten past. Instead of using shovels and brushes, astronomers use powerful telescopes to measure three key stellar properties: their motions through space, their ages, and their precise chemical makeup. Stars that form together from the same cloud of gas will share a distinct chemical fingerprint, a specific pattern of elements that acts like a family name. They also move together through the galaxy like a school of fish swimming in concert. By mapping these stellar families, we can identify stars that do not belong to our galaxy's original population. These cosmic immigrants are the survivors of ancient galactic collisions, the remnants of smaller galaxies that the Milky Way consumed billions of years ago. Their distinct chemical signatures and unique orbital paths are the evidence allowing us to trace them back to their original homes. This is how we discovered the Gaia sausage, the ghost of a massive dwarf galaxy that slammed into the young Milky Way, an event that fundamentally shaped our galactic core. We can even determine the sequence of star formation. The very first stars to form in the universe were composed of only hydrogen and helium. When they exploded, they seeded the cosmos with heavier elements. The next generation of stars incorporated these new elements, becoming slightly more metal-rich. By measuring the metal content of a star, we can place it in a generational timeline. This allows us to read our galaxy's history like a book, chapter by chapter, revealing a past filled with violent mergers and a steady enrichment of the elements that make our own world and us possible. This brilliant era of galactic construction is not destined to last forever. The cosmic dawn of star formation will inevitably give way to a long, slow dusk. Peer billions of years into the future, and the universe will be a profoundly different and far lonelier place. The primary engine of galactic change, the collision and merger of gas-rich systems, will grind to a halt. As dark energy relentlessly drives the expansion of space, the vast distances between galaxy clusters will stretch into an impassable gulf. Galaxies will become isolated islands, their gravitational reach no longer able to bridge the ever-widening voids. The raw material for new stars, the cold hydrogen gas, will also vanish. It will either be locked away in long-lived, low-mass stars, burned up in final bursts of creation, or blown entirely out of galaxies by powerful quasar feedback and stellar winds, lost to the intergalactic emptiness. Without fresh gas and without mergers to stir the pot, star formation will cease completely. The brilliant blue light of massive, young stars will flicker out across the cosmos, never to be seen again. What remains are the older, cooler, redder stars. They will continue to shine for trillions of years, but their glow is a fading ember. The galaxies they inhabit will steadily redden and dim, their vibrant spirals and ellipticals transforming into faint, ruddy ghosts. This is the era of degenerate darkness, where the dominant light will come not from stars, but from the faint residual glow of white dwarfs and neutron stars as they slowly cool toward absolute zero. The universe, once ablaze with the light of 100 billion galaxies, will quietly fade to black, a cold and silent epilogue to the fiery story that began with a single cosmic whisper. Woven through the vast emptiness between the stars is an invisible force, a ghostly web of magnetism. These galactic magnetic fields are unimaginably faint, millions of times weaker than a common refrigerator magnet, yet they permeate every cubic light-year of a galaxy's disk. They are the silent architects of the interstellar medium, tracing delicate patterns through the clouds of gas and dust. Their influence is subtle but profound, guiding the flow of material and shaping the very nurseries where stars are born. When a cloud of hydrogen begins to collapse under its own gravity, these magnetic fields provide a form of cosmic resistance, like invisible elastic bands that slow the process, helping to regulate the birth rate of new suns. They also act as nature's largest particle accelerators, trapping charged particles and whipping them to nearly the speed of light, creating the mysterious cosmic rays that constantly bombard our planet. But how can we possibly detect something so intangible, so ethereal? The key lies in starlight itself. As light travels through the dusty regions of a galaxy, the elongated dust grains align themselves with the magnetic field lines like countless microscopic compass needles. This alignment polarizes the starlight, causing it to vibrate in a preferred direction. By carefully measuring this subtle polarization with radio telescopes, astronomers can literally map the invisible magnetic skeleton of our own Milky Way and other galaxies, revealing the grand, sweeping lines of force that structure the cosmic void. Our solar system is not a stationary fixture in the Milky Way. It is a passenger on a grand orbital journey. The Sun, with all its planets in tow, travels along a vast circular path around the galactic center, moving at a breathtaking speed of over 200 kilometers per second. Yet, despite this incredible velocity, the scale of our galaxy is so immense that a single complete circuit takes an almost unimaginable length of time. From our vantage point here on Earth, the Sun has completed roughly 20 of these circuits since it first ignited. This timescale, known as a galactic year, stretches for about 225 to 250 million Earth years. To put that into perspective, the last time our solar system was in this particular position in the galaxy, the continents were fused into the supercontinent Pangaea, and the earliest dinosaurs were just beginning their reign. An entire galactic year has passed since the age of the dinosaurs began and ended. All of human civilization, from the first cities to the present day, has occurred in less than a single blink of this cosmic clock, a fleeting instant at the very end of the 20th orbit. This grand timescale recontextualizes our place in the cosmos, reminding us that while we measure our history in millennia, the galaxy itself keeps time in epochs. The vibrant heart of a galaxy can turn against itself, starving its own core of the fuel needed for new life. This process is known as inside-out quenching, and it is the cosmic equivalent of a city's central power grid failing first, with the blackout slowly spreading to the suburbs over billions of years. The primary culprit is often the supermassive black hole residing in the galactic center. When this monster actively feeds, it does not just consume matter quietly. It unleashes a ferocious wind of energy and radiation, a powerful feedback that acts like a colossal heater. This energy blast sweeps through the galaxy's inner regions, violently heating the vast reservoirs of cold hydrogen gas. Think of a pot of water on a stove. When the water is cold and calm, it can condense and form droplets, but if you turn the burner to its highest setting, the water boils into a hot, diffuse vapor that cannot easily coalesce. This is precisely what the black hole's feedback does to the star-forming gas in the galactic core. The gas becomes too hot and energetic to collapse under its own gravity, effectively shutting down the creation of new stars from the inside out. We can observe this dramatic transformation in distant galaxies. Astronomers use special filters to map where new stars are being born, and they see a clear pattern. The central regions of these quenching galaxies appear red and dead, filled with aging stars, while the outer spiral arms may still glow with the blue light of ongoing stellar nurseries. It is a slow, creeping death for a galaxy, a gradual dimming that begins at the very seat of its power and radiates outward, leaving a beautiful but sterile structure in its wake. While galaxy clusters represent the bustling cities of the cosmos, the space between them is an unimaginable emptiness. These are the cosmic voids, vast spherical regions of near-nothingness that can stretch for hundreds of millions of light years. If a rich cluster is a brilliant metropolis, then a void is a desolate continent, a territory so empty that it might contain only a handful of isolated galaxies. The scale of these voids defies easy comprehension. Traveling across one at the speed of light would take a human being longer than the entire history of complex life on our planet. Within these caverns, the average density of matter is only about 1/10 of the cosmic average, making them the universe's most underdeveloped real estate. The few galaxies that do reside there are often strange, lonely outposts, evolving in near-total isolation without the gravitational harassment or collisions that shape their cousins in the crowded clusters. This stark division between the crowded nodes and the empty voids is what gives the universe its sponge-like or web-like structure on the grandest scales. The luminous filaments of galaxies we see in deep surveys are simply the dense walls surrounding these immense, dark bubbles. What force could possibly arrange the cosmos into such a pronounced pattern of something and nothing? The answer lies once again with dark matter. In the early universe, gravity acted as a cosmic sculptor, but it worked in two directions simultaneously. It pulled matter into the dense hills that became clusters and filaments, and in doing so, it necessarily emptied out the regions in between. The voids are not a separate creation. They are the direct and inevitable consequence of structure formation itself, the negative space in the universe's great sculpture. This cosmic web, with its brilliant nodes and its profound emptiness, is the ultimate expression of how a nearly smooth beginning was transformed by gravity into a universe of stark and beautiful contrast. Those elegant spirals and serene ellipticals are not permanent identities. A galaxy's shape is more like a phase in its life, a single frame from a long and dynamic movie. The classification system we use is a snapshot, not a sentence. A majestic spiral galaxy, for instance, holds its form only as long as it enjoys a quiet, isolated existence. If a smaller galaxy passes too close in a gravitational encounter, the results are not destruction but distortion. The spiral's beautiful symmetry can be completely torn apart, its stars flung into a chaotic splatter, transforming it into an irregular galaxy. This is a temporary state of cosmic chaos. Yet, if that same irregular galaxy holds onto its rich reserves of gas and is left undisturbed for billions of years, its own rotation can gradually settle the turmoil. The chaotic splatter can slowly organize itself into an orderly, rotating disk, and spiral arms may once again emerge from the calm. This is the path from chaos to order. But the most dramatic transformation comes from a head-on collision. When two gas-rich spiral galaxies of similar size merge, the event is so violent it erases their disk structure entirely. The resulting gravitational turmoil randomizes the orbits of billions of stars, wiping out the spiral arms and sculpting a smooth, round, elliptical galaxy. The galaxy's type has fundamentally changed. Its history of violent union is now frozen into its very form. This means the universe is not a static museum of galactic specimens. It is a living gallery where every portrait is still being painted, and the subject can change its entire appearance based on the events of its long and turbulent life. At the very edge of our vision, we find the universe's first pioneers. The current record holder for the oldest known galaxy is an object designated JADES GSZ 130, a faint smudge of infrared light that represents a staggering look back in time. We are seeing this galaxy as it existed a mere 300 million years after the Big Bang, a cosmic infant in a universe only 2% of its current age. To spot such a faint object requires pushing our most powerful observatories, like the James Webb Space Telescope, to their absolute limits. Astronomers must stare at a single, tiny patch of seemingly empty sky for dozens or even hundreds of hours, collecting every precious photon that arrives from the edge of time itself. The light from JADES GSZ 130 has been traveling for over 13.4 billion years to reach us, and in that time, the expansion of the universe has stretched its wavelengths from visible and ultraviolet light into the infrared, a red shift so extreme it places it among the very first building blocks to emerge from the cosmic dark ages. This galaxy is not a grand spiral, but a small, compact, and intensely blue clump of stars, likely undergoing a ferocious burst of formation. Its existence at such an early epoch is a profound test for our models of cosmic evolution. How did gravity assemble so much material into a recognizable galaxy so quickly after the first stars flickered on? Finding these ancient galaxies forces us to refine our understanding of how structure emerged from the primordial soup, revealing that the universe got down to the business of building far sooner and more efficiently than we ever thought possible. Each new record breaker is not just a trophy, but a crucial data point from the universe's first chapter, challenging us to rewrite the story of how everything began. Our galaxy's vast gravitational reach extends far beyond its shimmering disk, capturing a retinue of smaller companions. These are the dwarf spheroidal galaxies, faint and ghostly collections of ancient stars that orbit the Milky Way like cosmic moths around a brilliant flame. They are the most common type of galaxy in the universe, yet they are so dim and diffuse they were almost missed entirely. Their discovery, however, led to one of the most persistent puzzles in modern cosmology, the missing satellites problem. When scientists run supercomputer simulations of how structure forms in a universe dominated by dark matter, they get a very specific prediction. The early cosmos should be teeming with countless small dark matter halos, the gravitational cradles that allow small protogalaxies to form. According to these models, our Milky Way should be surrounded by many thousands of these small, dark satellites, but when we look up at the sky, we only see a few dozen. The vast majority of these predicted satellites are simply not there. Where did they all go? It is as if we had a theoretical blueprint for a bustling city with countless small neighborhoods, but when we arrived, we found only a handful of villages and a great deal of empty land. This glaring discrepancy between prediction and observation has forced astronomers to reconsider their assumptions. Perhaps the smallest dark matter halos never managed to form stars at all, remaining completely dark and invisible to our telescopes. Or maybe the intense ultraviolet radiation from the first galaxies heated the cosmic gas so effectively that it prevented gas from cooling and collapsing into these tiny halos, stranding them as barren, starless clumps of dark matter. Solving this mystery is crucial because the number and nature of these tiny satellites are a direct test of our core understanding of dark matter itself. Their absence suggests that the story of how the smallest structures in the universe were built is still missing a vital chapter. But how can we possibly map the invisible cosmic web, the grand filaments of dark matter that guide the formation of galaxies? We cannot see this structure directly, yet astronomers have devised a brilliant method to trace its outlines using the most distant light in the universe. When they point their telescopes at a quasar, one of those brilliant active galactic nuclei shining from the edge of time, they do not see a pure, clean spectrum. Instead, the light is carved up, bearing the scars of its long journey through space. The quasar's intense beam of ultraviolet radiation passes through countless clouds of neutral hydrogen, gas that float in the vast voids between galaxies. Each of these clouds acts like a filter, absorbing a very specific wavelength of light associated with hydrogen. Because the universe is expanding, each cloud is at a slightly different distance, and thus its absorption line is shifted toward the red by a different amount. The final result is a spectacular barcode of hundreds or even thousands of dark lines, all superimposed on the quasar's rainbow. This dense, spiky pattern is poetically named the Lyman Alpha Forest. Each line is a tree, and together they form a forest that maps the distribution of hydrogen along our line of sight to the quasar. Since this hydrogen is believed to trace the underlying distribution of dark matter, the Lyman Alpha Forest gives us an indirect but powerful way to chart the cosmic web itself. We are not seeing the dark matter filaments, but we are seeing the neutral hydrogen that has pooled within their gravitational valleys, a cosmic fog that outlines the shape of the invisible universe. It is a ghostly imprint, a shadow play that reveals the architecture of everything. The space between stars is not truly empty, but filled with an invisible rain of high-energy particles. These galactic cosmic rays are primarily protons, the nuclei of hydrogen atoms, hurtling through the galaxy at nearly the speed of light. They are nature's most powerful atomic bullets, and their source lies in the aftermath of stellar death. When a massive star explodes as a supernova, it does not just fling debris into space, it creates a colossal shock wave that expands for thousands of years. This wave acts as a natural particle accelerator, far more powerful than anything we can build on Earth. It sweeps up stray atomic nuclei and electrons, trapping them in a turbulent magnetic field and boosting them to incredible energies. Once set loose, these cosmic rays do not travel in straight lines. They spiral along the invisible pathways of the galaxy's magnetic field, a chaotic journey that bounces them back and forth across the Milky Way for millions of years. This constant, invisible downpour has tangible effects. When these high-energy particles slam into the cold, dense gas of a molecular cloud, they can knock electrons loose from atoms, ionizing the gas. This subtle process helps initiate the complex chain of events that leads to the gravitational collapse of a cloud and the birth of a new star. Yet for all their creative potential, they also present a formidable danger. For astronauts venturing beyond the protective bubble of Earth's magnetic field and atmosphere, this relentless particle radiation poses a significant health risk, a silent hazard of interplanetary travel that must be carefully shielded against. This invisible rain is a reminder that a galaxy is not just a collection of luminous stars, but a dynamic system of interconnected forces, where even the death of a single sun can seed the future and challenge our dreams of exploration. Venture into the galactic core and you enter a realm of extremes. Within just a few hundred light years of the precise center, the star density soars to staggering levels. Here, space is so crowded that a single cubic light-year might contain over 1 million stars. If you lived on a planet in this neighborhood, your night sky would not be a scattering of points, but a continuous, blazing sheet of light brighter than 1,000 full moons. This stellar metropolis is not just home to ancient suns, it also hosts some of the most massive, youngest star clusters in the entire galaxy, like the spectacular Arches cluster, where stars are packed so tightly they are almost touching. Yet this brilliant chaos is overshadowed by two colossal and mysterious structures, the Fermi bubbles. These are titanic lobes of ultra-hot gas, each one reaching 25,000 light-years above and below the galactic plane, pouring out a powerful fog of gamma-ray radiation. Imagine two vast, ghostly balloons, each one large enough to contain a significant portion of the Milky Way itself, inflating from the core. Their origin remains one of the great puzzles of our galaxy. Did they form from a colossal feeding frenzy of the central supermassive black hole, Sagittarius, a star, millions of years ago? Or were they blown out by an immense burst of star formation, a firestorm of supernova on a scale we can barely comprehend? This region is a cosmic pressure cooker, a place where the fundamental forces of creation and destruction are amplified to an almost unimaginable degree, reminding us that the heart of our own galaxy is a deeply alien and violent place. The growth of a galaxy is a story of relentless accumulation. Imagine a graph plotting cosmic time against galactic mass, a chart spanning billions of years. In the early universe, the line begins low, dotted with countless small points, each one a fledgling proto-galaxy. These were the cosmic villages, mere fragments of what was to come. As the timeline progresses, the line curves steeply upward. Those isolated points begin to connect, merging into larger and larger blobs. This is the history of galactic mass assembly, a slow but dramatic buildup from modest beginnings to the colossal systems we observe in the present day. The primary drivers of this growth are twofold. First, there is the quiet, steady rain of pristine hydrogen gas from the intergalactic medium, a continuous trickle of new fuel. But the real leaps in mass come from the dramatic, violent mergers we have already explored. Each collision was a major acquisition, a corporate takeover in the cosmic economy, instantly doubling or tripling a galaxy's stellar content and dark matter halo. This process, however, was not uniform. The most massive galaxies we see, the giant ellipticals at the hearts of clusters, assembled their stars with astonishing speed and efficiency in the universe's first few billion years. They experienced an intense early burst of star formation, often triggered by a major merger that used up their gas reserves in a brilliant, fiery climax. After that, their growth was largely through what astronomers call dry mergers, the collision of gas-poor systems that added stars but did not spark new creation. In contrast, a galaxy like our Milky Way represents a slower, more extended growth history. It has grown through a series of smaller, wet mergers, cannibalizing gas-rich dwarfs and steadily accreting gas to form stars at a more measured pace across nearly the entire age of the universe. This timeline of mass tells a profound story of two different galactic lives, one of explosive early success and another of patient, steady building, both leading to the majestic giants that now drift through the cosmic dark. This delicate dance between creation and resistance is choreographed by turbulence. Deep within a galaxy's swirling clouds of gas and dust, the interstellar medium is far from a calm sea. It is a chaotic, supersonic maelstrom, a storm on a scale so vast it dwarfs our entire solar system. These are not gentle breezes, but shock waves racing at thousands of kilometers per second, stirred by supernova explosions and the fierce winds from massive stars. This cosmic chaos plays a surprisingly complex role in the birth of new suns. On one hand, turbulence acts as a powerful support system, a form of energetic pressure that pushes back against the relentless crush of gravity. A massive cloud of hydrogen might have enough mass to collapse under its own weight, but the violent, churning motions within it can keep it puffed up and stable for millions of years, like a perfectly whisked meringue that refuses to deflate. Yet, in its very randomness, turbulence also sows the seeds of its own downfall. When these chaotic waves collide, they can create incredibly dense knots and filaments, local pockets where the gas is squeezed together far more tightly than the surrounding area. In these specific, turbulent, made denser regions, gravity finally gains the upper hand. The localized pull becomes stronger than the internal pressure, and the knot begins to collapse, initiating the slow, inexorable process of star formation. The entire stellar birth rate of a galaxy is set by this intricate balance, a three-way tug of war between the disruptive force of turbulence, the restraining influence of magnetic fields, and the relentless, patient pull of gravity. It is a testament to the universe's complexity that the same violent phenomenon can both prevent a galaxy from using its fuel too quickly and create the specific conditions needed to light new fires in the dark. A galaxy's lifeblood is its cold, dense gas, But in the crowded core of a galaxy cluster, this vital resource can be violently torn away. The space between galaxies in these clusters is filled with a superheated plasma, the intracluster medium, and when a galaxy moves through this thin but incredibly hot gas, it experiences something known as ram pressure. Imagine sticking your hand out of the window of a car speeding down the highway. The force you feel pushing against your palm is a form of ram pressure. For a galaxy orbiting at millions of kilometers per hour through a cluster, that pressure is not a gentle breeze but a hurricane force gale. This relentless wind slams into the galaxy's own reservoir of cold hydrogen gas, the very material it needs to form new stars. The galaxy's own gravity struggles to hold onto this delicate, swirling cloud of fuel. The superheated intracluster plasma acts like a cosmic blowtorch, violently stripping the gas away and flinging it out into the void. The galaxy is left bleeding its own future into space. We can see this brutal process in action with objects astronomers call jellyfish galaxies. These are spirals caught in the act of being stripped, their gas pulled into long, shimmering tendrils that stream behind them like the ghostly tentacles of a cosmic jellyfish. Each of those trailing tails represents billions of suns worth of potential solar systems that will now never be born. This process, ram pressure stripping, is one of the most efficient ways the universe has of quenching a galaxy. It shuts down star formation not with a slow internal fade, but with a violent external robbery. The galaxy, robbed of its fuel, is left to slowly redden and dim, its spiral arms destined to fade as the last of its blue stars die out. It becomes a quiet fossil, a testament to the harsh realities of life in a crowded cosmic city. These ancient monsters present a cosmic timing problem. We now observe fully grown supermassive black holes with masses billions of times that of our Sun, shining as brilliant quasars when the universe was less than 1 billion years old. For gravity to build something so colossal from a single stellar remnant should have taken much, much longer. A star-sized black hole, left to its own devices, would need to feast continuously at a theoretical maximum rate for nearly the entire age of the cosmos to reach such a size. Yet these giants were already there in the cosmic infancy. How did they bypass the slow, steady growth and achieve such staggering mass almost instantly? One compelling theory suggests they skipped a step entirely. Instead of forming from a single dying star, they were born big. In the primordial universe, vast clouds of pure hydrogen and helium could have collapsed directly under their own immense weight. Without the heavy elements that help modern gas clouds fragment into many small stars, these pristine clouds might have collapsed into a single, monstrous object, a seed black hole that could be tens of thousands of times the mass of the Sun from its very first breath. This would give it a colossal head start, a king's portion of mass to begin its feast. Another possibility is a frenzy of rapid mergers in the crowded core of an early proto-galaxy. If the first stars were massive and lived short, violent lives, they would have left behind a swarm of stellar mass black holes. In the dense, chaotic environment of a young galaxy, these black holes could have sunk to the center, colliding and merging over and over in a violent cascade, quickly building up a supermassive core. Perhaps the truth combines both ideas, with direct collapse seeds forming in special, quiet regions, then merging and feeding furiously in the gas-rich nurseries of the first galaxies. The existence of these early giants forces us to reconsider the very first moments of cosmic structure, a time when the rules of growth might have been far more extreme than anything we see in the universe today. Even the central bulge of a galaxy hides a story of its past. These dense, spherical hubs at the heart of many spirals are not all created equal. They come in two distinct flavors, each telling a different tale of cosmic construction. On one hand, we have the classical bulge. This is the old guard, a relic of a more violent time. Picture a miniature elliptical galaxy sitting right in the galactic center. Its stars orbit in a chaotic, random swarm, buzzing around the core like a vast cloud of bees. This jumbled structure is a classic signature of a dramatic past, likely formed long ago from the violent merger of smaller galaxies or a single, catastrophic collision. The immense gravitational turbulence of such an event completely randomizes stellar orbits, erasing any orderly disk and puffing up the central region into this rounded, classical form. Its stars are typically old and red, a quiet population that witnessed the galaxy's most fiery chapter. But there is another, gentler path to building a bulge. The pseudobulge is an entirely different beast. It was not forged in the fires of a collision, but built slowly and patiently from the inside out. This structure forms through what astronomers call secular evolution, the gradual internal evolution of the galactic disk over billions of years. Instead of a chaotic swarm, the stars in a pseudobulge retain a sense of order, often rotating in a flattened, disk-like structure right in the galaxy's heart. The most telling sign of a pseudobulge is the presence of a central bar. This straight structure of stars acts like a cosmic funnel, dragging gas inward from the spiral arms and piling it up in a brilliant nuclear ring around the very center. This ring then ignites with intense star formation, making the pseudobulge a site of ongoing creation, often glowing with the blue light of young stars. So the next time you see an image of a majestic spiral galaxy, look closely at its bright core. Is it a classical bulge, a fossil of ancient chaos, or a pseudobulge, the product of its own steady internal growth? The answer is written in the motion of its stars and the light of its heart, a permanent record of the forces that shaped it. That faint, cold light bathing the entire cosmos holds the ultimate blueprint for every galaxy. Known as the cosmic microwave background, it is the oldest light we can observe, a fossilized snapshot of the universe when it was a mere 380,000 years old. Before this moment, the universe was a searing, opaque plasma, too hot for atoms to form, where light was constantly scattered by free electrons. But as the cosmos expanded and cooled, electrons and protons finally combined to create neutral hydrogen atoms. In that pivotal instant, the fog cleared and light was set free to travel across space. This ancient afterglow has been cooling and stretching for over 13 billion years, and we now detect it as a uniform microwave signal coming from every direction in the sky. But this background is not perfectly smooth. When we map it with exquisite precision, we see a tapestry of minute temperature variations, tiny patches that are ever so slightly warmer or colder than the average. These fluctuations are not random noise, they are the imprint of those primordial quantum ripples, the density hills and valleys from the universe's first moments, now frozen into this cosmic photograph. The slightly warmer spots correspond to regions that were marginally denser, where gravity had a little more to work with. The cooler spots were the slightly emptier voids. This is the cosmic seed catalog. Every galaxy cluster, every solitary spiral, every vast filament in the cosmic web can trace its origin back to a specific pattern in this ancient light. It is the universe's baby picture, and encoded within its faint whisper is the entire future structure of everything we see today. How staggering to realize that the grand design of 100 billion galaxies was already written in faint relief before a single star had ever ignited. The very stars above us are laboratories for alchemy, and one element in particular betrays this secret. Technetium is a heavy metal with a crucial property: it is fundamentally unstable. Every single one of its isotopes is radioactive, decaying into other elements on timescales far shorter than the life of a star. The longest-lived form of technetium has a half-life of only 4.2 million years. This is a mere cosmic blink, an instant compared to the billion-year lives of the stars we find it in. Yet, when astronomers analyze the light from certain giant stars known as asymptotic giant branch stars, the spectroscopic fingerprints of technetium are there, shining clearly in their atmospheres. This discovery was staggering. It means the technetium atoms we are seeing cannot be primordial leftovers from the birth of the galaxy. They would have decayed into dust eons ago. The only possible explanation is that these atoms were created very recently, forged in the searing nuclear furnaces deep within the star's own core. Powerful currents of convection then act like a cosmic elevator, dredging these freshly minted atoms up from the heart of the star and depositing them onto the surface for us to see. This is direct observational proof of a process called the S process, or slow neutron capture, where atomic nuclei slowly absorb neutrons to build elements heavier than iron. Each time one of these aging giants pulses and shudders, it breathes out a wind of gas enriched with these new elements, including technetium, into the surrounding space. This stardust will eventually become part of future generations of stars, planets, and perhaps even life. The presence of this ephemeral element is a live broadcast of galactic enrichment, a quiet but constant reminder that the story of the cosmos is not just written in the past tense, but is being composed in the fiery hearts of stars at this very moment. Every atom of your being holds a cosmic history. The calcium that strengthens your bones, the iron that carries oxygen in your blood, the very oxygen you are breathing at this moment, all of it was forged in a stellar furnace that no longer exists. These elements were not present at the universe's birth, when it was a soup of only hydrogen and helium. They were created under immense pressure and temperature, deep within the cores of massive stars that lived fast and died violently. When those stars exhausted their fuel, they did not fade quietly. They ended their lives in cataclysmic supernova explosions, scattering their newly forged elemental essence across interstellar space like cosmic gardeners sowing seeds. This stardust, enriched with carbon, nitrogen, and oxygen, then mixed with clouds of pristine gas. Over eons, gravity pulled these enriched clouds together, and from one such cloud, our Sun and its planetary system, including Earth, were born. So when you look up at the Milky Way, you are not an outsider gazing upon a distant spectacle. You are the galaxy itself, looking back at its own history. The carbon in your cells, the nitrogen in your DNA, the oxygen filling your lungs, all of it is recycled material, the legacy of generations of stars that lived and died over billions of years. We are not just inhabitants of this galactic city, we are its walking, talking archive. Our existence is a direct, physical continuation of the galaxy's own chemical evolution, a living testament to the fact that the cosmos is not a cold, empty void, but a participatory story, and we are a conscious part of its unfolding narrative. From a nearly perfect smoothness to a cosmos teeming with galactic life, our journey has spanned billions of years. We began with a universe of searing, formless energy, where microscopic quantum ripples were stretched into a cosmic blueprint by a fleeting moment of hyper-expansion. These faint whispers were given form by the ghostly anchor of dark matter, whose invisible wells gathered the first stars into fledgling galaxies. Through relentless collisions and majestic mergers, these chaotic building blocks assembled into the grand spirals and serene ellipticals we see today, their shapes a permanent record of a violent or quiet past. All the while, the mysterious pressure of dark energy has been scripting the universe's ultimate fate, pushing galaxies apart on the largest scales. This story is not just one of distant giants, but of our own intimate origins. The iron in your blood and the calcium in your bones were forged in the hearts of long-dead stars, scattered by supernova, and recycled into the cloud that became our solar system. We are not merely observers of this cosmic drama, we are a living product of it. The next time you find yourself beneath a clear, dark sky, look up, see that river of stars not as a static picture, but as a dynamic, evolving city, built over eons from chaos and guided by unseen forces. Let us know which of these 50 facts reshaped your view of the cosmos. Share your favorite cosmic revelation in the